So let's look now at logarithms. And logarithms will be a new function. And we're going to explore this logarithmic function, its basic properties and its domain, as well as take a logarithmic function and switch it to exponential and see how it relates to exponential. And that's important here. We're going to relate exponential and logarithmic functions to one another. Now we have already explored the exponential function. Now let's find the inverse of that function. And we've already graphed this function f of x equals 2 to the x, but let's just graph this one more time with a table of values where we take some x coordinates and find corresponding f of x coordinates. And if we remember the points we want to find, if we do -1, 0, and 1, that'll help us find our key points of 1/2, 1, and 2. And so we can easily plot those points on our graph like so, and we can do a sketch. We know we have a horizontal asymptote, and here is a quick sketch of our function f of x. Well, what if we want to take this function and find its inverse? And remember, the inverse of a function, the coordinates just switch. Instead of being x and y, it's now going to be y and x. So our new coordinates will just swap. Instead of being at -1/2, we'll be at 1/2, -1. Instead of being at 0, 1, we'll be at 1, 0, and 2, 1. And this would be our x coordinate for our inverse of our function. So now we can plot those points like this. And remember, the inverse of a function is a reflection across the line y equals x, which is that line right there. And then if we were to plot this graph, we could see the graph will look something like so. Take that same shape. And there's the inverse of the function. Here is f to the -1 of x. Now we could also solve the inverse algebraically. And remember, to solve this algebraically, we take our original function, f of x equals 2 to the x, make it y equals 2 to the x, switch the x and y around, and then try and solve for y. But this is where we have a problem. How do we get the y value out of the exponent? How do we solve for y? Now we're going to keep that in the back of our mind because we're going to look at this inverse and we can generalize for any base. Any base, we're always going to have certain key points. At 1, we'll always be at the base. At 0, we'll always be at 1. And at -1, we'll always be at the reciprocal of the base, or 1 over the base. Now, if those are the key points on the exponential, the inverse, well, the points just swap. b and 1, 1 and 0, and 1 over b and -1. Which means if we were sketching the graph of the inverse of y equals b to the x, we would just plot the points. We'd always go through 1, 0, and we'd always have a value up at some b and 1 and some 1 over b and 1 and get a sketch that looks like this. But again, the dilemma we have is how do we solve this for y? That's what we want to do, get an equation that y equals something. And this shape is actually what we call the logarithmic function. And that's how we relate. The inverse of an exponential function, we now call some other function a logarithm. And if we have something in exponential form, we can relate it to logarithmic form. We can go back and forth between the two. Now, here's the important thing about a logarithm as it relates to an exponential. First thing we want to notice is that the base in the logarithm is the same as the base in the exponent. The b's are the same. And if we're trying to find out what the exponent is equal to, remember we're trying to find the solution for that exponent, it's going to come from some y value. Y is going to equal some base to some exponent. And these are the relation between exponential and logarithmic form. And we're going to use logarithms quite a bit. So we have to know how to relate an exponential to a logarithm, how to switch from one form to the next. So let's just do our straight switch, and then we'll do a formal definition. Here is our exponential form. If we want to take it from exponential to logarithmic, well, it's pretty easy. We just follow the notation above. Log, the base stays the same, base 3. And what goes after the base is what's called the argument, which in this case would be 81 is equal to 4. So we have a base, the exponent, and what we call the argument. Just switching them around. Well, we can do that for another exponent. 5 squared is 25. We know 5 squared is 25. If we wanted to write that in logarithmic form, we would say log base 5 of 25 is equal to 2. So this allows us to switch from logarithmic to exponential form. And we know that the logarithm is the inverse of the exponential. But what a logarithm really is saying is the logarithm is the exponent, x in this case, to which some base, b, must be raised in order to get some other number, y. And we can write it in this form. Log base b of y is equal to x. The exponent that some base must be raised to give us the other number. Now you might think, well, why don't we just work with exponents? And we're going to work with exponents all the time. But we're actually going to find that if we switch it to this new function, logarithm, it's going to make a lot of calculations a whole lot easier. So we're going to look at logarithms, we're going to look at switching them around, and look at a whole bunch of rules. Well, we can actually use this swapping from exponential to logarithm to find a value for x. So this question is asking us 6 to some exponent x must equal the argument of 216. That's what this logarithm is asking us. 6 to what exponent is 216? And I just took the definition and actually just wrote it from logarithmic form to exponential form. Now what this allows us to do is just solve for x by getting a common base using our rules for solving exponentials. So 6 to the x is equal to, well, 216 is the same as 6 to the exponent 3. And what this now allows us to do is just work with our two exponents. X must equal 3. So we can take it out of logarithmic form and we can put it into exponential and use all our rules for exponents. And we're going to do quite a bit of that solving exponential and logarithmic equations. But the thing to keep in mind is the logarithm is just a function. And this function is just a graph. And we can find the graph of a logarithm by using our knowledge of an exponential function. We're going to explore these basic properties using our exponential function. Well, we've already done this a number of times. If we have y equals 10 to the x, our key points of 1, 0, and -1 will give us 10, the base, Always 1 and 1 over the base. Now, if we were looking at the inverse of that, the inverse, so let's just consider reversing them around, and the inverse can be written either way. X equals 10 to the y, or take it in this form and write it as a logarithm. Y equals log base 10 of x. Doesn't matter which way we write it, we mostly are going to write it as a logarithm, but it just switches the points around. 10, 1, 1, 0, 1/10, and negative 1. So when b is greater than 0, we can get those points. And if we were doing a sketch, we could say here is 1, 0, 10 and 1 will be way out here. 1/10 and negative 1 is somewhere down here. And we have a graph that looks like so. What if the base is between 0 and 1? Well, we realize with the exponential, it doesn't change our key points. Still 1, 0, negative 1. Still the base, 1, and the reciprocal of the base, which in this case will be 2. So if we want the inverse, we'd be at 1/2 and 1, 1 and 0, and 2 and negative 1. And we can take those points and create a sketch. And that sketch then at 1, 0 would look like so. When we're at 1/2 and 1, well, probably somewhere up here like this. And 2 and negative 1 down like so. And we get a sketch like this. And there is our sketch of that graph, the inverse of the exponential, or the y equals log base 1/2 of x. Now from these two sketches, we can actually determine some of the properties of a logarithm. And one of the properties we want to look at is the domain of a logarithm. Now, since the inverse of an exponential function is a logarithmic function, the domain of the logarithmic function corresponds to the range of the exponential function. And if we think about this, it's pretty straightforward. Domain is the x values, and the x values in the logarithm correspond to the y values in the exponential. They just inverse, switch those around. So if we think of our exponential function, if we just do a quick little sketch, our exponential function looks something like that and has a range greater than 0, which means the domain for a logarithmic function, the possible x values, correspond to the range of the exponential. So that tells us that x in our logarithm must always be greater than 0. It must be a value that's positive. And if we think back to these graphs, what that means is we have an asymptote. And this time, though, the asymptote is a vertical asymptote. A vertical asymptote, because the domain must always be a positive x value. So that's going to become very important as we get into logarithms, that the domain, the possible x values, can only be greater than 0. So how do we apply this to a situation? Well, here's our logarithm, and we want to find out what is the possible domain of this logarithmic function. Well, the domain is going to come from this piece of the graph. And if we think about the sketch of the graph, the vertical asymptote was at x equals 0. Now this is telling us that the graph has been translated 2 units to the right, which means our horizontal asymptote must get translated 2 units to the right. And that means that our values in our logarithm must always be greater than 2 for this particular logarithm. Now we can do it pictorially using a picture, but there's an even easier way. When we have a logarithm, whatever's in the brackets must be greater than 0. So we could just take that argument, set it greater than 0, solve for x, and we'll get the exact same answer. So it can come from either the picture or the argument, and we're going to find when we do the next example that the argument is way easier to solve. We just take that argument, set it greater than 0, and we can find that x in this case must be greater than 1. Now there's only one other piece we have to consider in an example like this. We also have an x in the base. And if you remember the restriction on the base must be greater than 0 and it must not equal 1. Anytime we're dealing with a logarithm, we have to consider both base and argument. So we have one criteria here of x must be greater than 1. Well, we must now take our base and consider the restrictions on that x. X plus 2 must be greater than 0, which means x must be greater than negative 2. There's our second inequality. And we have one more criteria to measure, that x plus 2 can't equal 1, which means x cannot equal negative 1. And there's our 3 criteria. But now we have to consider these 3 criteria on a number line to find our restriction. Our first criteria, if this is our number line, here's 0. First criteria tells us x must be greater than 1. So x must be in that region. Our second criteria tells us x must be greater than negative 2. Like so. Our third criteria tells us x cannot equal negative 1, which is this point. And when we have multiple restrictions on our domain, we have to consider the domain is where all of the criteria are met. And in this case, all of the criteria are met in that region. And if that's the case, then our restriction is x must always be greater than or equal to 1. The other criteria don't matter because if it's greater than 1, it's not going to equal negative 1, and it's obviously going to be greater than negative 2. So they get a little more complex as the base and argument contain the same variable, and we're going to do many more examples like this in class.